All right, so let's work this problem of a coin on a turntable. If you can't picture a turntable is just a fancy word for a record player. Okay, a 5-gram coin. As I work through this beginning sentence, I will make note of the givens. However, I will not write them down just yet because the first thing it's going to ask us to do is draw some stuff. And so I have the places we'll be drawing right below. So, okay, a 5-kilogram coin, so that's the mass, is placed on a horizontal turntable 15 centimeters from its center, so that's going to be its radius, as shown in the diagrams below. The coin does not slip, and the turntable completes one revolution every 800 milliseconds. So that one rotation every 800 milliseconds, it's tempting to call that, one delta theta is 1. And, I guess the time for one rotation, delta t, would be 800 or 0.8 seconds. However, we're going to treat that as if that is just an omega. So that omega is one rot every 800 milliseconds. Okay. Anyway, we'll deal with that when we get down there. Okay, so on the side view, draw and label the arrows coming out of the coin to represent the forces acting on the coin. On the overhead view, draw and label arrows to represent the instantaneous acceleration and velocity of the coin. Okay, so on the side view, what we need to do is we need to think about what are these directions. Okay, we need to think about the directions of the coordinate system that's acting on the coin. And so the first thing that you want to do is you want to recognize that the R direction, the radial direction, is always out from the center of the, the spinning. So in this case, that's happening at the center of the record or the center of the turntable. And so the radial direction is out from there. So we'll do that with the dotted line. Okay, and then we want to recognize that, so there's one more direction. There's an up-down direction, which in this case, the temptation is to call that, I don't know what you might want to call it, but that is the Z or the Z direction. And you can put that coming out of your coin, or you can put it coming out of the center of the record. Some people kind of prefer to come out of the center of the record. I don't think it really matters. I think the idea here is that you are saying that it's coming from, kind of the origin of this coordinate system, which would be out at the center of the record. So we'll go with that. Okay, let's see. So now we have to analyze the forces on this coin. So I'll do these with solid lines, and you'll notice that going down, of course, we have gravity, force of gravity. Going up, we have a normal force. And anywhere we have a normal force, we have a friction force. In this case, the friction force, when you turn this, when the turntable is on, the friction force is going to cause the coin to turn. And so it's going to be causing it to turn towards the center. Okay, now you might say, well, why is that? Why the center? And it's quite simple. If you imagine that there's no no friction at all, then what's going to happen is this thing is not going to turn, and the coin's just going to keep going straight into or out of the into as drawn. Okay, so anyway, so what it is doing is it's causing it to turn. Okay, on the overhead view, so if we go over here, we'll look at the overhead view. Okay, and what we want to do on that particular coin is we're going to draw the same axis, or one of the same axes, right? We still have that R axis coming out from the center. Okay. However, there's also a tangential direction, which is going in whatever direction would cause this thing to spin counterclockwise. Okay, the temptation here is to say, oh, well, the T direction is the direction the coin is turning. In this case, that happens to be true, but there's no reason why the coin has to go in the positive T direction, just as you do not have to go in the positive X direction in a problem with X, Y. Okay, so now that I have those two things and I have put them on my on my board, they want me to label the acceleration towards the center, the instantaneous acceleration and the velocity of the coin. I'm going to do these in different colors because I want to remind myself that these are not things that can be added to each other, right? They're separate items. Okay, we'll start with the velocity, and we notice from the picture on the in the center that this thing is spinning kind of in a counterclockwise manner. So that means that at an instant, the coin is going upwards. Okay, it's got a tangential velocity, which I'm going to label as v sub t. Okay, that v sub t is going to be changing constantly, always turning to the left or towards the center, and that is because its acceleration is towards the center, and so we will call that a sub c. Okay, we will note that those are different colors because they are totally different and unrelated. Well, they're not unrelated, but you can't add them to each other. Okay, Okay, so let's start doing this one by one. So the first thing that I want to do is I want to set up my givens. Okay, and I think, you mentioned this earlier, but, the mass is 5 grams. Now, note that this is probably my most commonly missed conversion. So if it's got a 5 gram, that means you need to move the decimal place 3 places to get to kilograms. So it'd be 0.005 kilograms. We've got a radius of 15 centimeters. So centi means we need to move the decimal 2 places, 0.15 meters. Okay, and then we've got an omega. Okay, and the omega is 1 rotation every 800 milliseconds. So I'm just going to call that 0.800 seconds. And I'll just quickly convert that. And we'll get 7.8540 rads per second. All right, so now we have to start figuring out, let's see, a few of the things that this problem is asking for. So it says determine the magnitude of the instantaneous velocity of the coin. I will note that, I guess let's get all the required. So A, we want to know the instantaneous velocity. Now, I want to note that this only has a tangential velocity, so I'm just going to call it V. I'm not going to put that little t on there just because there's no reason really here because there's only one velocity, so I don't need to distinguish it. So I'm going to write V equals 0. Okay, equals question mark, excuse me. Okay, and then B, what do we want? We want to determine the magnitude of the instantaneous acceleration of the coin. Okay, that's the acceleration towards the center. Again, there's only one acceleration to this coin. It's not speeding up tangentially. However, I'm going to leave that C there just to remind myself that that is the acceleration towards the center. Okay, number C, we're going to want to know the weight of the coin. Okay, the force of gravity of the coin. Okay, number D, we want to figure out the normal force. Well, if you've been paying attention in this class, you already know the normal force and the friction and the weight on this particular object will end up being equal. Let's see, number E, we want to determine the friction force between the coin and the desk. Okay, force of friction equals question mark. F, determine the minimum coefficient of static friction between the coin and the platform. So the reason they asked for the minimum here, again, that's mu, but the reason they asked for the minimum is that if it was any less, the coin's just going to slip off, and none of this is actually going to work out, right? My AC will not be enough to keep the coin on the table or on the turntable. Okay, and then G, and this is more of a conceptual problem. If you move the coin slightly farther out, would it stay on the platform or slip off? So I'll say if R increases, does it slip? I'll just write slip question mark. Okay, cool. So let's start powering through these one at a time. Okay, the instantaneous velocity of the coin. Okay, so the way that I'm going to get the instantaneous velocity is I just solved for omega. So I'll say, okay, so V equals R omega. This is off the equation sheet. So I'll say V equals 0.15 meters times the omega, which we solved for, which is 7.8540 rad per second. Remember, those radians aren't really a unit, so don't really get scared when we get something weird looking. And I'm getting 1.1781. That's meters per second, and we'll go ahead and round that to 3 sig figs. So I have 1.18 meters per second. Okay, box and move on with your life. Okay, determine the magnitude of instantaneous acceleration. Okay, the acceleration, okay, we note that this is a centripetal acceleration. It is not accelerating tangentially, and because it's just going around constantly at the same speed. So this could be v squared on r. That is a possibility. However, I'm going to go to r omega squared. And the reason for that here is, you could use either one as long as you didn't make an error in the A part. However, since omega was a raw value, I'm going to use that one here. So my radius is 1.15 meters, and my omega is again 7.8540 rads per second. I'll square that, and my AC will be equal to, I'm getting 9.2528 meters per second squared, which I will round to 2 sig figs to be 9.25 meters per second squared. Okay, now note that if the direction of that one is inwards, but we are not, didn't ask for the direction, just wanted the magnitude. Okay, determine the weight of the coin. Okay, well that's, almost child's play, right? Force of gravity equals mg. So force of gravity equals 0.005 kilograms times g, which is 9.81 meters per second squared. So the force of gravity is 0. Let's let's see, 0.0491 newtons, right? Okay, and that's already a 3 sig fig, so we'll kind of keep it there. Okay, part D. Determine the normal force between the coin and the disc. If you can't see it already, we will go ahead and do this formally. And so we will stare at this free body diagram, and we will note in the vertical, and we will note that the sum of the forces in the z direction, the z direction, the up and down direction, equals mass times acceleration in the z direction. So we get the normal force going up, we got the gravitational force going down, and we're going to leave that right-hand side alone for now. Okay, so let's see. Let's expand. The normal force minus mg equals, we'll say maz. It's not accelerating up or down. So the normal force equals mg, which we solved a second ago. So the normal force equals 0.00491 newtons. Okay. All right, let's see what else we got. Part E, determine the friction force between the coin and the desk. Okay, so again, we're gonna go and we're gonna look at this little free body diagram we have here, and I'll do the sum of the forces in the r direction this time equals ma sub r. Okay, so let's see here. The forces in the r direction, the only one is the force of friction, and is going in the opposite of the r direction, so it'll be negative force of friction equals, we're going to leave that right-hand side alone for now, MAR. So we're going to still call this negative force of friction equals, let's see, M. And then in place of A sub R, I'm going to write a negative because this thing is accelerating inwards in the opposite direction of R. And I have a few choices here. I can either use A sub C, I can use R omega squared, or I can use V squared on R. At this point, I think I did already solve for A sub C. So I will use A sub C here. Okay, that's the least common answer that you would use here. 90% of the time you use V squared on R, maybe 9% of the time you use R omega squared, and every so often you will have already calculated A sub C for some reason. Okay, so let's go ahead and solve for this. Okay, so we'll kind of do a little Storm-L there, and then so algebraically we will turn those things positive, and the force of friction equals 0.005 kilograms. Times that, we'll use all the sig figs there, 9.2528 meters per second squared. And so the force of friction is 0.046264 newtons. And if we round that to 3 sig figures, 0.0463 newtons. Okay, such small numbers. Of course, it is just a tiny little coin. Okay, determine the minimum coefficient of static friction between the coin and the platform. Okay, so how are we going to do that? Well, we've got the normal force, we've got the force of friction, which means we have this equation, the force of friction equals mu times the normal force. Cool. All right, so let's see here. So mu equals the ratio between the force of friction and the normal force, if we do the algebra there. So if I plug these numbers in, I get, using all of my sig figs here, I end up with, let's see, it looks like I'm going to end up with 0.94320, and to 3 sig figs, it'll be 0.943. Okay, so in other words, very sticky, right? Because it has to be between 0 and 1. 1 is the maximum, stickiness. So that's as good as we're going to get. Okay, the G part, which is really interesting, and it says, if R increases, will this thing slip? So if we move the coin from the position that it's at, 15 centimeters, and we move it to 18 or 20 or whatever, what is it more likely to slip or to stay where it is? Okay, and so I think the way that you should think about this is, if we go back to this force of friction equation right up here, okay, let's see, I'm going to bring it over here, and we'll say the force of friction equals mass times acceleration towards the center. Okay, so if we go farther out, what happens to the acceleration towards the center? Does it get bigger or smaller? If the AC goes up, then the force of friction will not be strong enough to hold it where it is, right? So there's two real options for how we calculate the A sub C. One is V squared on R. The other one is R omega squared. The temptation is to do V squared on R. It's easier for us to think about V squared on R. However, the problem here is this. If I increase R, then obviously the denominator will get bigger. However, by being farther out, farther from the center, we will note that the velocity also increases, which means the numerator will also increase. So if you can kind of visualize it, you can see that both v and r, they both increase linearly as r increases. And because the top is squared, that means it's more important than the bottom. However, that can be kind of sketchy and iffy logic if you can't see that these are both increasing linearly. So instead, what I would propose to do is I would propose to use r omega squared logically. Because if r increases, the omega stays the same, but the r goes up, which means the total acceleration is increasing. And if the total acceleration is increasing, then we would need more friction in order to make it happen. There's, friction is not going to be able to increase. It is at its, whatever its max might be. So therefore, it's going to have to, eventually slip off if you move it further out. Okay, that's all I got for today. So I hope you guys are doing well. Take care of yourselves. Remember, physics is awesome. Physics is cool. It's interesting, but you are more important. Okay, take care of yourselves out there. Okay, bye.